Here is a diagram circuit left over from the previous lesson. I now want to modify this diagram. I want to redraw it and place it in the center of the screen. I also want to reposition this resistor, and the resistor is going here. We no longer need the fusing circuit for this lesson, and we no longer need a picture of the battery. What we are about to do is replace the battery picture with a battery symbol. This one. Here is a battery cell, a single battery cell. It has a positive plate and a negative plate. A cell is nominally 1.5 volts. A fully charged cell will show 1.6. A cell in poor condition, 1.2. There are 8 cells in this battery. Let's put the other 7 in. 2, 3, 4, 5, 6, 7 and 8. The negative terminal is now here and the positive here. So 8 cells times 1.5 volts equals 12 volts. This is a 12 volt battery, standard for the intruder alarm industry. We know the voltage, 12 volts, and we know the resistance in the circuit is 60 ohms. But what we do not yet know is the current. But that is not a problem, because by knowing 2 of the numbers we can use Ohm's law to work that out. You'll remember that in a previous lesson you were taught how to use the Ohm's law pyramid. Let's demonstrate and use that again. If you were to cover the V like this, the pyramid reveals I alongside R. This tells us that V equals I multiplied by R. If we now want to know how to calculate the current, we find the formula by covering the I. Now the pyramid reveals the V over R. So I equals V divided by R. And finally, if we were to cover the R for resistance, the pyramid reveals the formula, and that is R equals V divided by I. We want to calculate the current in this circuit, so we don't need the formula for voltage and we don't need the formula for resistance. So we see that I equals V over R. We know that the battery is 12 volts, so that number can go in here, and we know that the resistance is 60 ohms. That number, 60, can go in here. The formula now tells us that I equals 12 divided by 60, therefore I equals 200 milliamps. Let me remind you that there are 1000 milliamps in 1 amp. 200 milliamps is the same as saying 0.2 amps. In the alarm industry, however, we usually express this as milliamps. 200 milliamps. Once again, I want to tidy up the slide a little. So let's explore. How will this circuit be affected if we add another resistor? Let's add another resistor to find out. This is the new component, and as you can see, it too has a value of 60 ohms. With two resistors in the circuit, the overall resistance will change. This is the formula for calculating resistances in series. The formula is RT, meaning resistance total, RT equals R1 plus R2 plus R3 plus R4, etc. In other words, in a series circuit, the resistances are added together. There are only two resistors in this circuit, so let's reduce the formula. There. Now we need to label these resistors. This is R1 and this R2. We can see that R1 is 60 ohms, so let's put that number into the formula. R1 is 60, and so is R2. Let's do the maths. RT equals 60 plus 60, therefore RT equals 120 ohms. So the circuit resistance has doubled. It is now 120 ohms. Let's park that figure down here and let's see how it affects the current flowing in the circuit. Once again, we go back to our formula. I equals V over R. We know that voltage is 12 volts, but this time the resistance is not 60, it is 120. Let's put that number in. So the formula is telling us that the current is equal to 12 divided by 120. Therefore, I equals 100 milliamps. To analyse that, what we are saying is that by adding the second resistor, we have decreased the current in the circuit from 200 milliamps to 100 milliamps. But what else? What else is there to learn from this circuit? Well, there is the phenomenon of voltage drop. Let's investigate that with the use of a multimeter. Let's plug in the wires to our multimeter and then we will be able to start. Now we're ready. I am going to switch on the multimeter by turning the knob from the off position to the symbol that says DC voltage. That is this one here. From off to DC voltage. The probes are not yet connected to the circuit, so the voltage reading is 0. Let us connect the black probe here. And when we connect the red probe, you will see that the reading on the meter will change. And it changes to 12 volts DC. Now let's see what happens when I move the probe from here to here, to the other side of the resistor. If we look at the multimeter, it now reads 6 volts. Let's examine why that is. We had 12 volts here, and we only have 6 volts here. So this means we have lost 6 volts across this resistor. Then what about this point here on the other side of resistor 2? We know this to be 0 volts, and how do we know that? Well, we know because the wire is directly attached to the battery negative terminal here. So this 0 volt reading means we must have lost another 6 volts across the second resistor, and indeed we have. We don't need the multimeter for the time being, so let's switch it off and remove the leads. Time to mention the law relating to voltage drop, and that law is called Kirchhoff's law. Kirchhoff's law states that in any DC series circuit, the sum of the voltage drop across each component in the circuit is equal to the supply voltage. We worked it out previously, so we know that the current flowing through this circuit at the moment is 100 milliamps. And we also know that that current is flowing through both resistors. Let's see if we can confirm the voltage drop mathematically. The voltage formula is the one we need to use, and we are going to apply it to resistor 1 across this resistor here. Once again, here is the formula. V equals I times R. So we are looking for V, and we know that the current to be 100 milliamps and the resistance 60 ohms. If we do the maths, therefore, V equals 6 volts. This confirms the size of the voltage drop across R1, and we will get the same result across R2 because the current and the resistance are identical. So, to reinforce what it is we have just learnt, we have discovered that although the current through these two resistors is the same, that is 100 milliamps, the voltage across each resistor is only 6 volts. I want to take this a little further because I think this voltage drop can be best explained visually. I will attempt to do this using light bulbs to demonstrate. But first I need to change what you see on the screen. Okay, so here is a light bulb. As you can see, it also has a resistance of 60 ohms. I am going to replace the resistor with a light bulb holder. Let's screw the light bulb in and see what happens. Now we've done that, you can see that the light bulb shines nice and brightly. And the reason it is bright is because we have 12 volts powering this device and 200 milliamps flowing through the circuit. If we were to add another light bulb in series, and I'm going to do that in a moment, then we'll see what difference it makes. I am about to add a new light bulb holder, and as I do that I am breaking the circuit. This will mean that the other light bulb will go out temporarily. There. Here is the new light bulb. Let's screw this one in and find out what happens. Now we see that the light bulbs are not as bright. When one was in, it was this bright. Now they are both dim. This is because there was previously 200 milliamps in this circuit. Now there is only 100 milliamps and only 6 volts across each bulb. This ties in with Kirchhoff's law. So if we add together the voltage drop across each component, in this example it is 6 plus 6, the total should add up to the supply voltage. And it does, 12 volts. End of lesson.